Hey, physical science students. I thought I would just take a little while and go over all of the examples in Module 9 and just demonstrate how to do them. I'm going to be pretty quick, but hopefully this video will be helpful if any of you are having trouble with the math involved. So let's begin with Module 9's first example. Example 9.1. And feel free to just skip ahead to any of the examples that are more pertinent to you because I'll be doing these in order. All right, a car travels 78 miles down the highway. It takes the car 1.2 hours to travel that far. At what speed is the car traveling? So this is a speed problem. They're asking for its speed. So we need the formula for speed. And speed, hopefully you know, is going to be distance divided by time. You always want to use the formula whenever you can in math because then you can just plug in the information in the proper places where it's labeled in the formula. All right, so it says that a car travels 78 miles down the highway. So we know our distance is 78. So I'm going to write S equals and then 78 miles, always include your units, in place of distance. And it says it takes 1.2 hours to get there, divided by 1.2, and then the unit hours. Now I just have to divide 78 by 1.2, and when we do, we end up with 65. I'll just assume you can use a calculator and do that, or that you can do the math on your own. I'm not going to take the time to show my work there. So 78 divided by 1.2, speed equals 65, and the units you're left with are miles divided by hour. In other words, miles per hour. That's the speed of the car. Now let's do part B of example 9.1. It asks, what is the speed of the car from the previous problem in meters per second? And they give you a couple conversions, which is that 1 mile equals 1,609 meters. And we also are given that 1 hour equals 3,600 seconds. Okay, so we're going to take our original numbers and convert, so we have 78 miles and 1.2 hours, and we're going to convert 78 miles into meters. So 78 miles, we're going to put it over 1 as we always do in unit conversion problems because we need a fraction. Now we're going to multiply it by something where in the numerator, it's going to have the unit we want, and in the denominator, it's going to have the unit we want to cancel. All right, so times 1609 meters, which is the unit we want, and that's over 1 mile. And when we multiply this out, I'll save you the time and just let you know that if you entered that in the calculator or multiplied it out by hand, you would get 125,502 meters. All right. Now what about 1.2 hours? We're going to take 1.2 hours over 1 times, we want the thing we're going to cancel out in the denominator and the thing we want to keep in the numerator. There's 3,600 seconds, we're told, in an hour. And so what's 1.2 times 3,600? That's going to be 4,320. And our unit, because we can cancel hours, is seconds. All right, so now our 78 miles per hour is 125,502 meters per this many seconds, 4,320. I don't really need my original information anymore. I can just divide and I'll have my answer. So what is 125,502 divided by 4,320? I'm glad I don't have to do this mentally. The answer is going to be those two divide out to 29.1. And I am left with a unit meter and second, meters and seconds. So I could write it like that, or I could write it, with meters over seconds, numerator, denominator, that's fine, either way. All right, that's example 9.1, and now we're going to do example 9.2. All right, example 9.2, it says, two cars are traveling down a road. The first car is traveling north at 55 miles per hour. So here's the car number one. And for these, it really helps to draw a picture, I think. And we'll say it's going north at 55 miles per hour. And the second is a few hundred yards behind. So car 2 is behind, and it's also traveling north, but it's going at 45 miles per hour. Okay, so what is their relative velocity? And to review, velocity is speed with direction. So it's going to be like miles per hour north or something like that. But if you're giving relative velocity, then you get to go even easier, and your direction can be toward each other or away from each other. So are these cars going to be traveling toward or away from each other? That's a good question. And you see that they're moving in the same direction, and when cars or any objects are moving in the same direction, then you figure out their relative velocity by subtracting their speeds. If they're moving toward each other, you add their speeds, but they're going away from each other. I didn't mean toward each other. If they're moving in opposite directions, you add their speed, but if they're moving in the same direction, you subtract their speeds. So we're going to subtract, and let's say 55 minus 45, and these are miles per hour, but 10 miles per hour. That's the relative speed, but we need a relative velocity. We need to know what direction they're moving relative to each other. So they're actually going to be getting farther apart, because even though they're going in the same direction, this one's moving faster and it's ahead of the other one. So they're going to be getting gradually farther and farther apart at the rate of 10 miles per hour. So 10 miles per hour away from each other. And that's your answer. Example 9.3. Suppose a ball is falling. A person with a radar gun measures its velocity to be 2.0 feet per second straight down. Just 0.3 seconds later, he measures the velocity again and finds that it is 11.6 feet per second straight down. What is the ball's acceleration? So we need a formula here. Acceleration equals the final velocity minus the initial velocity divided by time. They tell us the final and initial velocity and the time, so we just need to plug those in to that formula. All right, so let's do that. The final velocity, in other words, how far the ball is going at the end, they said was 11.6 feet per second straight down. And we don't have to write directions into this, although that is useful information. We have to write the units for sure. So feet per second. And we're going to subtract the initial velocity. So how fast was it going when it started? That was 2 feet per second. And how long did it take to get from the final to the initial? That was 0.3 seconds. If you like, I can stick a 0 there. All right, so in order to subtract these, they have to be like terms. Are they? Yes, feet per second, both of them feet per second. So I'm going to carry this down. Acceleration equals 11.6 minus 2 is 9.6 feet per second over 0.3 seconds. All right, so what's 9.6 divided by 0.3? That's going to be 32, and I'll carry this down. Acceleration equals 32, and we have feet over seconds, and then in the denominator is seconds. So feet divided by seconds divided by seconds. That's actually going to work out to feet per second squared, so I can rewrite this as 32 feet slash seconds squared. You might be asking, how does it become seconds squared? Here's how. So if I had 32 feet over seconds, and then I divided it by seconds, that's the same as saying times 1 over seconds, right? So then what we do is we multiply what's in the denominator, and seconds times seconds is seconds squared. So that would be the same thing as 32 feet over seconds squared. And that's the answer I got down here. It's just written a little differently. And we've actually just calculated the rate of free fall, which is 32 feet per second squared. Example 9.4 is another acceleration problem, so I'll keep this acceleration formula up there. Remember, acceleration is final velocity minus initial velocity divided by time. It's really good to memorize all of these formulas. So this one says, a rock is dropped from a bridge into a river. It starts out with 0 initial velocity, and it hits the river 2 seconds later, traveling with a velocity of 19.6 meters per second downward. What is the acceleration? All right, it's telling us then, if it started with 0 initial velocity, it's not actually moving. It has 0 meters per second of velocity. So let's plug that in, and that's going to be our initial velocity. So minus 0 meters per second. And it says that 2 seconds later, it hits the water at 19.6 meters per second. All right, so we know that 19.6 meters per second is its final velocity, because that's when it hits the water 2 seconds later, and the time is that 2 seconds later. All right, so we've decoded the problem. We have our equation now, and we just got to work it out. 19.6 meters per second minus 0 meters per second, that's going to be easily figured out. That's 19.6 meters per second. So carry that down. And we're going to divide that by 2 seconds. All right, what's 19.6 divided by 2? The answer there is going to be 9.8. And we keep our units, meters per second divided by seconds. And as I demonstrated with the last problem, that's going to be meters per second squared. So 9.8 meters per second squared. And that's your answer. And I forgot to mention that the answer to example 9.4b also should include the direction downward. Same thing with example 9.3, because with acceleration you always have to give direction as part of your answer. So when something is falling, then it's easy because your direction is simply downward. All right, moving on to example 9.4. This one says, a bicyclist is traveling down a road at 18 feet per second to the east. The cyclist sees an obstacle in the road ahead, so he hits the brakes. In 1.8 seconds, the cyclist has come to a complete halt. What is the cyclist's acceleration? Now, did you hear a final velocity in there? It's a little bit coded, but hopefully you're able to figure out if he came to a complete halt, then he ended at 0 feet per second. So final velocity, 0 feet per second, and we're going to subtract from that the initial velocity, which was, it says he was traveling down the road at 18 feet per second to the east. All right, so 18 feet per second. Now already you might be seeing something a little troubling, that you're going to get a negative acceleration, but don't worry about that, it'll all work out in the end. Now we have to divide it by time, which is how long it took him to go from 18 feet per second to 0, and that was 1.8 seconds. All right, no unit conversions needed or anything. 0 minus 18 is, of course, going to be negative 18. What's 18 divided by 1.8? That's going to be quite easy to do. We end up with 10. Acceleration equals 10 feet per second divided by seconds, aka negative 10 feet per second squared. So how can you have a negative acceleration? And we're not going to use the term deceleration because that's not really a scientific term. But what we have is we have a guy who is going east at a certain velocity, but then he slams on the brakes, which means he's accelerating west. All right? He's accelerating in the opposite direction. So instead of saying negative 10 feet per second east, we can say the equivalent, which is 10 feet per second west. So a negative acceleration is actually just a positive acceleration in the opposite direction. Kind of an interesting thing to think about. All right, next acceleration problem, we have example 9.5. A sports car travels from 0 to 60 miles per hour north in 6.1 seconds. What is this acceleration? All right, so again, if it doesn't seem like they gave you all the information, they really did, because if he goes from 0 to 60 miles per hour, that's a very concise way of saying that he started with 0 miles per hour and went to 60. So 60 is his final. And his initial is 0. And that was in 6.1 seconds. Okay, so we got a bit of a problem here, which is that we have inconsistency in the units. We have hours and seconds. And they want your answer to be in hours. And this is going to actually result in a really crazy number. So let's convert seconds to hours. 6.1 seconds. And we're going to turn that into hours. So we want hours in the top, and we want seconds in the bottom, so it'll cancel. All right? And in order to do that, we need to use the conversion 3,600 seconds per hour. And so that gives us, instead of 6.1 seconds, we get 0.00169 hours. Weird numbers going on. All right, so I'm going to rewrite this with that new information. 60 miles per hour minus 0 miles per hour over 0.00169 hours. So now we have consistent information all the way through, same units, so we can proceed. 60 minus 0 is, of course, 60. Oh, I'll write this over here so we don't run out of visible space. All right, 60 divided by 0.00169. When you divide by a decimal, the number actually gets bigger. So that's going to give you a really large number. You're actually going to get 35,000 503 miles over hour, aka 35,503 miles per hour squared. Well, that problem really took up a lot of space. And you might be thinking, oh my gosh, how is a car so fast that it could go from 0 to 60 and then its acceleration is that? Well, think about this. What is miles per hour squared? Like, what is that really saying? Hours per hour? So what they're saying is that it can go from 0 to 60 miles in this many hours. Miles per hour in this many hours. So it's got a rate of 60 miles per hour. And if every 0.00169 hours, it increased by that same amount, by that 60 miles per hour, then every time this elapses, then you're going to be going 60 miles per hour faster. So, or to take it back to the original unit, every 6.1 seconds, then basically 12.2 seconds is going 120 miles per hour. And then 18.3 seconds is going 180 miles an hour. And if it did that every 6.1 seconds, then it actually would, by the end of an hour, be going 35,503 miles per hour. Now, is that realistic for a car to actually maintain that kind of acceleration? No, but for a moment it is under that kind of acceleration, but it wouldn't realistically continue that way. So that's what this information actually means. Okay, we're on to the last one. Congratulations on making it so far. We have experiment 9.6 here, example 9.6 here, and it says a young woman is standing on a bridge overlooking a river. If she drops a rock from the bridge and it takes 1.2 seconds for it to hit the river, how many meters did the rock fall? This one is going to be a little different because we're asking for the distance it fell, not its acceleration. We actually know its acceleration already because we know that when an object is in free fall, it accelerates at 9.8 meters per second squared down, or same thing, 32 feet per second squared down. So that's the acceleration due to free fall. And to calculate the distance that something falls in free fall, we use this formula. Distance equals 1/2 times acceleration, which is our free fall acceleration, times time squared. All right, so we already have all the information we need. The woman's on the bridge, and it takes 1.2 seconds for the rock to hit the river. So let's just fill this out. D equals 1/2 times, in our acceleration, we're dealing with meters, so that's going to be 9.8 meters per second squared, down, of course, times, and then our time is 1.2 seconds. And we're going to square this. Now that means we're going to take 1.2 and square it. So when you square 1.2, you get 1.44, and you're also going to square seconds. So to carry that down, distance equals 1/2 times 9.8 meters per second squared times 1.44, which is when you square 1.2, seconds squared. And you might be like, oh, wait a second, this is bad because now we're going to end up with like seconds to the power of 4. Well, no, because meters per second, seconds squared here is actually in the denominator. So I'm going to rewrite this. We're dividing by it, meters divided by seconds. All right, and now I can put this over a fraction, and now we have units that are a little bit more properly aligned for our purposes. So I can cancel seconds squared and seconds squared, and that's good because we're looking for a distance, right? Distance doesn't have any time involved. So now we have 1/2 times 9.8, or sorry, well, that's correct, yeah, 1/2 times 9.8 times 1.44. And so let's just do the numerator first, although you really could do it all at once. 9.8 times 1.44, that's going to be 14.112 meters, and we're going to be multiplying that by 1/2, so just divide that by 2, and our answer is that the distance equals 7.056 meters. All right, and you can't see that very well. I'll write it up here, actually, so you can see it better. 7.056 meters. Thanks for watching this video. I hope it was helpful. God bless, and I look forward to seeing you next time.